4.2 Antiderivatives as Areas. Part 1, Riemann Sums. Southwestern College, Professor Maria Olivas. Antiderivatives as areas. Objectives. Use rectangles to approximate the area under a graph. Find the area under a graph and use it to solve real-world problems. Section 1. Area and Riemann sums. Consider this problem. Find the area of the region enclosed by the parabola y equals 1 plus x squared. The vertical lines x equals 1 and x equals 3 and the x-axis. Okay, so I've highlighted where it says the parabola y equals 1 plus x squared in yellow, and I've highlighted x equal 1 and x equal 3 in green, and I've highlighted where it says the x-axis in blue. I've also drawn a cloud around where it says the x-axis, and I've drawn an arrow pointing to the right to y equals 0, and I wrote horizontal line because remember that the x-axis can also be represented by the equation y equal to 0, and it is a horizontal line. For our picture, we're going to draw a coordinate plane. We're going to focus on quadrant 1. I have labeled the x-axis, and I've also labeled the x-axis with the equation y equal to 0. I have also drawn tick marks on the x-axis from 0 to 3, separated by a scale of 1. I'm also drawing the parabola y equal to 1 plus x squared and vertical lines at x equal to 1 and x equal to 3. And I am labeling those vertical lines with the equations. I'm also labeling the parabola y equals 1 plus x squared. And I'm only drawing the parabola in quadrant 1. I'm going to shade in yellow the area that is enclosed by the graph of the function y equal to 1 plus x squared and the x-axis, and in between x equal to 1 and x equal to 3. So this is the area that we are looking for. We want to find this area of the region enclosed, and I have drawn a box around the words find the area, and I'm writing down the word area inside of that yellow shaded region that is bounded by the graph of y equal to 1 plus x squared, the x-axis, and x equal to 1 and x equal to 3. Our strategy for this is going to be, since we know how to find the area of a rectangle, we will divide the region into rectangular strips and add the area. So for our estimate 1, we're going to use 4 left endpoint rectangles to approximate the area. So I'm going to redraw the exact same graph that I had drawn up above right here. So I'm going to draw once again the coordinate plane focused on quadrant 1. I'm going to draw that parabola, only the section that is in quadrant 1 of y equal to 1 plus x squared. I'm going to label my x-axis by little tick marks separated by a scale of 1 from 1 to 3. So I've got 1, 2, 3 there, and I'm also going to draw the vertical lines at x equal to 1 and x equal to 3. And I have labeled my parabola or my function with y equal to 1 plus x squared. So now that I have my graph here, I am ready to start setting up this problem so that I can find the area, or at least approximate the area. I'm going to need to use 4 left endpoint rectangles, and I have highlighted the 4 left endpoint rectangles in yellow. I am going to first start off by labeling what my n is going to represent. My n is going to represent the number of intervals, or sometimes people like to call this also subintervals. And this is determined by the number of rectangles that we're asked to use. Since we're asked to use 4 left endpoint rectangles, my n is going to be equal to 4. And this is going to be within the closed interval of a and b, and for us, that closed interval is going to be from 1 to 3. So n is going to be equal to 4 because we're going to be using the 4 rectangles. And I'm going to label my delta x, which represents the width of each one of these rectangles, as b minus a all divided by n. In this case, it's going to be 3 minus 1 all divided by 4, which is 2 divided by 4, which reduces to 1/2. Or another way that I could write that would be 0.5. So my delta x, which is equal to 1/2, and can also be written as 0.5, that's going to be my delta x. And I have shown you right here by drawing a little line segment representing delta x above, right below my graph in between 1 and 1.5. And I have labeled this as delta x is equal to 0.5. I'm also going to label the little tick marks separating these by 1.5 and 2.5 so that you can see exactly where the widths of each one of my rectangles are going to be. So now we're ready to start drawing our rectangles. So we're going to go ahead and do that. Where it says 4 left endpoint rectangles, I'm going to end up drawing my 4 left endpoint rectangles so that each one of the 4 upper left-hand corners of the rectangle lies right on top of the graph of y equals 1 plus x squared. Now I know these rectangles might not look exactly the same in width, but they are each 0.5 in width. And these are, once again, left endpoint rectangles because I've drawn a red cloud around left endpoint, and I've drawn an arrow pointing towards the largest rectangle's upper left-hand corner. And I drew a little dot there, and I wrote down the word left. I'm going to shade all of these rectangles in yellow so you can see the area that we're going to be finding. So looking at this area, you could probably see that this is going to be an underestimate from the actual area because there are little pieces at the top of these rectangles that those areas are not going to be accounted for. Once again, this is an approximation. Now we need the height of each one of these rectangles. The height of the smallest rectangle is going to be represented by f of 1. I'm going to represent my function instead of y equals 1 plus x squared. I'm going to rewrite it as f of x equals x squared plus 1. So that means exactly the same thing. It will just be easier for me to refer to the heights as f of 1 instead of referring to the y. So that's why I'm going to rename it. So that first height, once again, I said is going to be represented by f of 1. I'm also going to shade in that part that is not going to be found in green so that you can see that this actually represents an underestimate. So I'm shading in green that leftover area part that I will not be finding the area of. I am going to go ahead and also erase the equations that I wrote here, the y equals 1 plus x squared and the f of x equals x squared plus 1, so that I have more space to write on the right-hand side. I will rewrite that equation for that function on the left-hand side here, right next to the y-axis and in between the y-axis and the parabola. So in quadrant 1. So I wrote f of x equals x squared plus 1 and an arrow pointing down towards the function. Let's go ahead and write down how we find the area of a rectangle. So the area of a rectangle is going to be equal to length times width, which is L times W. And now for this particular problem here, because of the way my rectangles are set up, I think it would be nicer if we wrote instead of L, H for height. So I went ahead and I circled the L and I wrote right beneath it H times W. Instead of the L, I put H, and I'm pointing a little arrow up at the H and I wrote down the word height, so you know that represents the height. Okay. Let's go ahead and write A for area, equals 0.5, which represents the width. I've highlighted 0.5 in blue, and also I've highlighted the delta x equals the 0.5 that was right below the x-axis in blue, and I've highlighted w in the formula in blue. Let's go ahead and write a equals 0.5 times f of 1, which represents width times the height, plus 0.5 times f of 1.5. This would represent our second rectangle going from left to right. I'm going to go ahead and move my area of a rectangle formula over a little bit to the left-hand side and upwards so that I have more space to write here. All right, so now continuing, plus 0.5 times f of our next rectangle's height would be f of 2, plus 0.5 times f of 2.5 is going to represent the height of the last and fourth rectangle that we have here. And then we're going to close the parentheses there. So that's going to be how we find the area of the 4 rectangles. Okay, for our next line, let's write a equals 0.5, open up a set of square brackets and write f of 1 plus f of 1.5 plus f of 2 plus f of 2.5, and then close our square brackets. What I've done here in this line is we factored out the 0.5. A equals 0.5 times, open up a square bracket, and here we're going to put the value of f of 1. F of x equals x squared plus 1, therefore f of 1 is equal to 1 squared plus 1, which is 1 plus 1, which is 2. So we're going to insert a 2. So we're going to write 2 plus f of 1.5. F of 1.5 is just going to be equal to 3.25. And I'm not going to show the work for that. You guys can do that in the calculator. Plus 5 plus 7.25 and close the square bracket. All right, I'm going to go ahead and just move over our work that we showed here for our f of x and f of 1. So it's out of the way. I think I'm going to have to just delete this. So we can just move it over here and delete it so it's out of the way. We showed you how to find it. Now you know how to find that work. A equals 0.5 times, open up a square bracket, and if we add up everything inside the square brackets, we'll get 17.5. And here for our last step, A is equal to 0.5 times 17.5 is going to give me 8.75. And we're going to go ahead and box that in. That is going to represent our approximate area. Now let's go ahead and write down some sigma notation here. I'm going to write down sigma, which is a capital Greek letter, right, for sigma. And we're going to write the sum from I equal to 1 up to 4 of f of x sub I times delta x. And this kind of here, what this represents is my general form of writing the sum of all of these rectangles using sigma notation. I'm going to highlight the delta x in blue so that you can see, you can make this connection of where this is. I'm also going to draw a little cloud around the delta x and an arrow pointing towards the 0.5 that I had in the very first row of work that I had here for this problem. I'm going to highlight the f of x sub I in green, and I'm going to draw a green cloud around it, and I'm going to draw an arrow here pointing at the f of 1, but of course it's not just the f of 1, right? It's also the f of 1.5, the f of 2, the f of 2.5. It was all of those y values that we came up with. But I've just highlighted the first one as an example here to show you where it's represented here in the work. We are ready to do our estimate 2. In this estimate, we will use 6 left endpoint rectangles to approximate the area. So we will begin by drawing our graph, same one we used in estimate 1. I'm going to highlight the words that say 6 left endpoint rectangles. I'm going to draw my coordinate plane. I'm going to draw the graph of my function in quadrant 1. And this is the function y is equal to x squared plus 1. I'm going to draw 3 tick marks on the x-axis that are separated by a scale of 1. This represents 1, 2, and 3. I'm going to draw my vertical lines at x equal to 1 and x equal to 3. This is going to represent the enclosed region of the area I am trying to approximate. So I'm going to go ahead and circle the 6 where it says 6 left endpoint rectangles, because I need that 6 that represents the 6 sub-intervals that I'm going to try to create here in my graph. So I'm going to have delta x equal to b minus a all over n. My closed interval from 1 to 3, that's where I'm going to get the values for a and b. A is going to be equal to 1, b is going to be equal to 3, and my n is going to be equal to the number of rectangles, which also represents the number of sub-intervals, so that n is equal to 6. So delta x is equal to 3 minus 1 all over 6, which is equal to 2 over 6, which is equal to 1/3. I'm going to use the fraction in this estimate because 1/3 as a decimal is a repeating decimal, and I think it'll be easier to work with the fraction. Let's go ahead and find these little sub-intervals. I'm going to add in more little tick marks in between 1 and 2 and 2 and 3. So in between 1 and 2, I've got 4/3, I've got 5/3, and in between 2 and 3, I'm going to have 7/3 and 8/3. Now we are ready to go ahead and draw our rectangles. So there's 1, there's 2, 3, 4, 5, and then one more will make 6. So I'm drawing these rectangles in from left to right. And each one of these rectangles has the upper left-hand corner that lies directly on the graph of my function. So now we are ready to shade in the area that encloses the area enclosed within the rectangles in yellow. This is the area that I'm going to find, and this is going to represent the approximate area that is enclosed under the graph of the function all the way to the x-axis in between the interval from 1 to 3. All right, I have finished shading in or highlighting in yellow that area within the rectangles. I'm also going to label the height of the first rectangle, the smallest one, the one that's all the way on the left-hand side, as f of 1. And I'm going to highlight that height in green. So remember that we do need to find the height of each one of these rectangles. So A, which is area, is going to be equal to 1/3 times, and I'm going to open a square bracket, f of 1 plus f of 4/3 plus f of 5/3 plus f of 2 plus f of 7/3 plus f of 8/3, and then we're going to close the square brackets, and that's going to represent the heights of each one of our rectangles from left to right. A will equal, or A will approximately equal, and this is already, once you have plugged this into your calculator, you should get 9.370 as an approximation for that area. And if we wanted to represent this using sigma notation, we would write the sum from I equal to 1 all the way up to 6 of f of x sub I times delta x. So although we have not learned how to find the exact area of figures with curved edges, we have learned how to find an approximate area for these regions. And this example in the estimate 2, where we had 6 rectangles, this, because there are more rectangles, is going to represent a closer approximation than when we used 4 rectangles. So ultimately, what this teaches us is that if we have more rectangles, we'll have a better approximation. So these rectangle approximations are called Riemann sums. The form of a Riemann sum is going to be the following. Once again, I'm going to write that capital sigma, that Greek letter, and we're going to write this as the sum from I equal to 1 up to n of f of x sub I times delta x. And this is how we would represent that Riemann sum when there is a finite number of rectangles. To find the exact area, we need an infinite number of rectangles. So I'm going to write the limit as n goes to infinity of the sum from I equal to 1 up to n of f of x sub I times delta x. So if we have infinitely many rectangles, this will give us the precise area. I'm going to go ahead and box this in because this is a pretty important concept here. So this idea is going to allow us to always find that exact area, especially in those more difficult problems where curvature is involved. But for now, let's do a few more examples involving Riemann sums. Let's go on to example number 2 here. Example 2. A test plane flies in a straight line with a positive velocity v of t in miles per minute at time t minutes, where v is a differentiable function of t. Selected values of v of t are shown in the table below. So here we have a table where our independent variable is t, which represents minutes, and our dependent variable is going to be v of t, which is miles per minute. So for t minutes, we have a table. I'm going to read it from left to right, the values of t, which are going to be 0, 5, 10, 15, 20, 25, 30, 35, 40. Then the values for v of t, I'm going to read also from left to right, is 7.0, 9.2, 9.5, 7.0, 4.5, 2.4, 2.4, 4.3, 7.3. Use a Riemann sum with 4 subintervals of equal length and values from the table to approximate the area under the curve for the given time interval. Using correct units, explain the meaning of your result. But the key part here is that we need to use a Riemann sum with 4 subintervals of equal length and values from the table to approximate the area. So why don't we go ahead and highlight that part in yellow so it stands out and we know exactly what it is we're trying to do here. So let's go ahead and highlight that part in yellow where it says Riemann sum with 4 subintervals of equal length and values from the table to approximate the area. I'm also going to highlight where it says t minutes in the table, because that's going to represent our independent variable, and that's important. And I will also be highlighting the smallest value under t and the largest value, which is 0 and 40. So that means our interval here is going from 0 to 40. So I'm going to write the closed interval from 0 to 40, where 0 represents our A and 40 represents our B. Now I'm also going to put a cloud here where it says 4 subintervals of equal length, because that's telling me that my n has to be equal to 4, because we're going to have 4 subintervals. Now we can go ahead and find our delta t. So delta t is going to be equal to b minus a all divided by n, which is going to be equal to 40 minus 0 all divided by 4. And this is equal to 40 divided by 4, which is equal to 10. So that's going to represent the length of each one of our subintervals. So now we can write down our A. Our A is going to represent area. A is going to be equal to 10 times, open square bracket, V of 0. And then here, if we put plus, in order to get my next T value, I'm going to go up here to my table, and I'm going to have to add 10. I've just circled the 10, and I drew an arrow pointing towards the 0. I've circled the 0 in the table. 0 plus 10 is equal to 10. So 10 is going to be my next T value. I've highlighted the 10 in green. And then 10 plus 10 is 20. I've highlighted the 20 in green. And 20 plus 10 is 30, and I've highlighted the 30 in green. And then I've gone back and I've also highlighted the 0 that's in the table in green. So those represent those T values that I will be substituting in for V of T. So I'll have plus V of 10 plus V of 20 plus V of 30, and then I can close my square bracket, and that's going to be my area, or the approximation for my area. So A is going to be equal to 10, open square bracket, and now I'm going to go back up to the table, and I'm going to highlight in blue the corresponding Y values, or V of T values here. So I'm going to have 7 plus 9.5 plus 4.5 plus 2.4, and then close the square bracket. So I need to add up all those values and multiply it with 10. So A is equal to 10 times 23.4, which is equal to 234. We don't know the units for this. This is what we need to figure out next. So I'm just going to go ahead and point an arrow up to where the unit should be written to, and underneath that I'm going to write units with a question mark. I drew a coordinate plane over here on the right hand side, focusing on quadrant 1 to help us with the units. I'm going to circle where T is equal to 0 and V of T is equal to 7.0, because that's representing my y-intercept. So that is 0, 7. So I'm going to draw a tick mark on the y-axis, and that's going to represent kind of my y-intercept there. And I'm just going to draw a random function coming off here, and then a straight line coming down where T is equal to 40. So now I'm going to label on the x-axis 0, and I'm going to label T, well, because this represents the t-axis really, and I'm going to label the V of T axis. And I'm going to highlight the V of T axis, and I'm going to write down the units that represent that axis, which is miles per minute. And then on the T axis, I'm going to highlight that in blue, and I'm going to label those units. So those units are minutes. Now we're trying to figure out the area underneath the curve. I'm drawing a rectangle here, just one random left end point rectangle here, and I'm shading in partially under the curve, and I'm shading in my rectangle because we're trying to figure out the units that are being represented there. So I'm going to draw a little line here for the width and the height of this rectangle. The height is definitely miles per minute, or miles over minute. The width is minutes. So if I wanted to find the area of this rectangle, I would need to multiply my width times the height. So miles over minute times minute over 1. The minutes would cross cancel, and my product would just be miles. So the units, I'm drawing a cloud over the miles, around the miles, and my units for this answer are going to be in miles. I'm going to highlight in green the rectangle, and I'm going to point the miles to the green rectangle that I highlighted in green here. That's what the units are. So let's go ahead back to our 234 answer. I'm going to erase where I wrote units with a question mark, and I'm going to write in the units of miles after the 234. And now I can box my answer. Now we still need to explain the meaning of our results here. So 234 miles for what? Right? I went ahead and wrote in the 40 here in my graph, the 40 minutes. And then this is going to tell me that all of this shaded region, and I'm shading everything now under the curve in green, is going to represent the total number of miles, right, traveled in 40 minutes. So I'm going to point an arrow to my 234 miles, and I'm going to write here the explanation of my results, or the meaning. This is the distance the plane traveled in 40 minutes. And I'm going to draw a cloud around that because that is also part of my answer. That is explaining the meaning of our result. Okay. Okay, we're ready to go on to example number 3. Example 3, the rate of fuel consumption in gallons per minute recorded during an airplane flight is given by the function shown below. A table of selected values is given. I am going to go ahead and describe the graph and the table that are shown below. So here we have a graph that is focused in quadrant 1, and on the x-axis, or in this case the t-axis, we have time. And the time is represented in minutes. I can tell by looking at the table because in the table it says t and then minutes in parentheses. And then the y-axis, or the r of t-axis, is going to be rate of fuel consumption. On the t-axis, we have a scale of 10, and we have from 0 up to 90 shown in tick marks, separated by tens. On the r of t-axis, we have from 0 to 70 scale of 10, from 10, 20, 30, 40, 50, 60, up to 70. And then we have a graph of a function. These points on this function are given, that are represented here, are given in the table. So I am going to go ahead and read off the table values. So here we have a table, a 2-column table. In the left-hand side, we have t minutes, our independent variable. And on the right-hand side, we have r of t, which represents gallons per minute. So for t, I'm going to go ahead and list the t values going down from top to bottom, and then we'll list the r of t values going down from top to bottom. So first for t in minutes, we have 0, 30, 40, 50, 70, 90. And for r of t, we have 20, 30, 40, 55, 65, 70. That means the ordered pairs that are shown in the graph are going to be 0, 20, 30, 30, 40, 40, 50, 55, 70, 65, and 90, 70. And the ordered pairs are connected by the curve that represents the function r of t on the graph. Beneath the graph and the table of values, there are some instructions for us to follow. It says, use a left Riemann sum with the 5 subintervals indicated by the data in the table to approximate the area under the curve. Interpret your result. Since it's asking us to use a left Riemann sum, this means we will be using left endpoint rectangles to find the approximation for this area. And it also stated that we needed to have 5 subintervals, which means we will need to have 5 rectangles. It also said that it needs to be indicated by the data. So this problem is going to be a little bit different from the other problems we've done before. I'm going to go ahead and highlight the key information here where it says use a left Riemann sum with the 5 subintervals indicated by the data in the table. I'm also going to highlight in green so it stands out more, indicated by the data in the table and the 5. So these 5 rectangles are not going to be the same size in width because we're going to have to go by the numbers that were given to us in the table and not by delta x or delta t in this case. Here I'm circling in red the 30, the 40, the 50, the 70, and the 90 in the table. That's going to help me when I need to find exactly how wide each one of my rectangles is. So now I am drawing my rectangles, and as I'm going over, I'm making sure that I bring the line down for my rectangle right at those numbers that I circled. So notice here, as I'm drawing, this is the 4th rectangle I'm drawing. I'm coming down right at 70. And then this next one, this is my last rectangle I'm drawing. I'm coming down here right at 90. So if you look at these rectangles, they do not all have the same measurement in width. Some of them, these are different from each other. I'm going to highlight the area within the rectangles. So this is the area that I'm looking for. So finding this area is going to be just slightly different from the other problems we did. We're still finding area, but since we don't have the exact same width for each one of these rectangles, I won't be able to factor out the width the way I did before, right? My delta x, or in this case, my delta t, because we don't have one in this case. I wrote A here to represent area. And I put A equals, and we're going to write down, basically we're going to have to find the area of each one of these individual rectangles. For the first rectangle, the one that's most on the left, I have highlighted the base or the width, and I have drawn a line under it, and I wrote 30. I've also highlighted the side, the height, and I wrote 20 next to it. So I'm basically going to have to multiply 20 times 30. I also need to be aware of the units. So for t, it says time next to the axis, and I know that those units are in minutes. And the units for r of t are going to be gallons per minute. And I knew this because it said so in the table. I've circled the part on the table where it said gallons per minute, and I drew an arrow pointing at the gallons per minute that I wrote on the side of the axis. And I also drew clouds around my units that I wrote on each one of these axes so that it stands out and you know what the units are. All right, so for the first product here, A is going to be equal to 30 times 20. And I'm going to write down the units right beneath it so we know what the units will end up being. We're going to have minutes over 1 times gallons over minute. The minutes will cross cancel and we will just be left with gallons. So when you're finding the area of this problem, you're actually finding an answer that represents gallons, like total number of gallons. So let's make sure we remember that. All right, now we're going to put plus. The next one's going to be 10 times. I'm just going to go ahead and find the difference to each one of these t's over here on the table. So if I subtract 0 from 30, I get 30. If I subtract 30 from 40, I get 10. If I subtract 40 from 50, I get 10. And if I subtract 50 from 70, I get 20. And 70 taken away from 90 is 20. So for this one here, for the first one, notice I put a 20 inside the parentheses to multiply with the 30, and I got that 20 from the y values under the r of t. Over here, for the 10 that I put plus 10 is going to get multiplied with the 30, with the y value that's right next to it, right? And then we got plus 10 times 40, plus 20 times 55, plus 20 times 65, and that's going to be the total right there. We're going to go ahead and find that product of each one of those and add them together. A is going to be equal to 600 plus 300 plus 400 plus 1,100 plus 1,300. So let's go ahead and add all of those numbers up together, and that's going to give me a total of 3,700. And let's not forget our units. This represents gallons. Let's go ahead and box that answer in. So This answer, the 3,700 gallons, what it actually means, I'm just going to write it down here right beneath, 3,700 gallons of fuel represents the total fuel used by the plane over 90 minutes. And I went ahead and I boxed in that sentence that I just wrote down because that was part of the instructions, because it did say interpret your results, and this is what's happening here.